right, so hopefully chapter 4 was a good chapter. Let me start with section 5.1 and see what happens here. I move the microphone, and hopefully that doesn't mess things up, but I think that makes any difference to you. So in section 5.1, we're going to look at the graphs of polynomials, and it's not a deal breaker if you don't know exactly what a polynomial is. Let me give you an example of things that are not polynomials. And then I'll try to show what a few polynomials. So a function like this, f of x equals 3x to the negative 1 plus 4x squared plus 5. The exponent of negative 1 makes this not a polynomial. To be a polynomial, all the letters have to have exponents that are integer exponents, positive integers at that. So here's another example. I'll do a different name. G of x equals 4x to the 1/2 plus 7. This fractional exponent also makes something not a polynomial. So if something's written in expanded form, the only exponents I can want to see are positive integers. Here's another example of something that's not a polynomial. Although I don't see any fractional or negative exponents, I see an x in the denominator of a fraction. That also makes something not a polynomial. This is actually considered a rational function, because rational meaning fraction. So if you have an x buried in the denominator of a fraction, that's not a polynomial as well. Let me give another name, maybe something like this. So these are all not polynomials. So an x with a negative exponent, an x with a fractional exponent, an x in the denominator of a fraction, or an x under a radical make all of these not polynomials, and they're not going to be the types of functions that we're going to study in section 5.1. Here's an example. These are polynomials, something like this. F of x equals 3x squared plus 9x minus 4. What this has in common, or what this has that makes it a polynomial, is that the only letters have positive integer exponents. There's not a letter under a radical or in the denominator of a fraction. Something like this x plus 2 quantity squared, that's still a polynomial. It's not, it's a factored polynomial, but if I wanted to, I could expand this by foiling, and I'd get x squared plus 2x plus 2x plus 4, which is x to the 4th plus 4x plus 4. So if I expand the parentheses, I get every x term, or every term with a letter, having a positive exponent. It's okay to have fractions for coefficients, something like this. 1/3 x to the 4th plus 5x cubed plus 6x minus 9. That would still be considered a polynomial. The 1/3 as a coefficient isn't keeping this from being a polynomial. If something's written in expanded form, if all the letters have positive integer exponents, no exponents are negative or fractions, no x's in the denominator of a fraction, and no x's under a radical sign, basically you have a polynomial. So section 5.1 focuses entirely on polynomials and a bit on the graphs of polynomials. So there's more, unfortunately, that we have to understand before we get into the section. And we need to know something about called the degree of the polynomial. A function like this polynomial, say 3x cubed plus 7x squared plus 6x plus 1, I'm just randomly making these up. I would say this is a, how about 13x cubed as opposed to 3x cubed. I don't want 2 3's here. I'd say this is a third degree polynomial because the highest exponent is 3, and I'm going to graph two functions that likely don't look anything like the particular function, but one is potentially similar to the graph, the other's impossible to be the graph. So like this graph and this graph. The left one is potentially, probably not going to be exact, but it's potentially close to the graph of this function. And the next one is, I'm absolutely guaranteed this is not a chance of being close to the graph of f of x. Very specifically, when I look at a polynomial, polynomials graphs usually have humps in them or turning points, and a third degree polynomial, it could have less, but it will have in its graph, will have no more, or at most 2 turning points. You get at most 1 less turning point than the degree of the polynomial. And if I look at the first graph I drew, this is considered a turning point. It's a maximum point. And this is considered a turning point. This graph has 2 turning points. Which means it could come from a function that has an exponent 1 or more higher. So the minimum degree of the polynomial that makes this is 2 plus 1, which is 3. If I look at this graph, this I'll say TP for turning point here. There's a turning point here. There's a turning point there. So this one has 3 turning points. And when a function has 3 turning points, the smallest degree of the polynomial that can make it is a 4th degree polynomial. It turns out that there's something about the graph that would tell me this would even have to at least be a 5th degree. But I'd say this, for now, this would have to at least come from a 4th degree polynomial. You can't get 3 turning points from a polynomial that's 3rd degree. If a 4th degree polynomial can make 3 turning points. You always take the highest, the degree of the polynomial, which is the degree of the term with the highest exponent, subtract 1. That would give me the most turning points the graph can have. So a 3rd degree polynomial can have at most 2 turning points. Let me do another example like this. So if I gave a function like this, f of x equals negative 3x to the 4th plus 2x cubed plus x squared minus 5x minus 1. This is a fourth degree polynomial. Because the highest exponent is a 4. And that I know from just some theory that the graph can't have more than 3 turning points. It could have less, but it can't have more. So the maximum number of turning points is 1 less than the degree of the polynomial. The degree of the polynomial is the highest exponent if the polynomial is expanded. So like this graph, 1, 2, 3, 4. This graph has 1, 2, 3, 4, 5, 6 turning points. That definitely can't be this graph. So this can't be close to the graph of f of x because it has 6 turning points, and this graph could only have 3 turning points. It could have less than 3 turning points. For instance, this is potentially the graph of this function because it doesn't violate. I don't know what the graph of the function looks like, but this doesn't violate it because this right here only has 1 turning point, and a fourth degree function could have 1, 2, or 3 turning points. It can't have more than 3 turning points, but it could have less than 4. It could have 1, 2, or 3. It has to have at least it has to have a turning point. If it doesn't have any turning points, I'm going to take that back. It doesn't even have to have a turning point. But this is potentially, it could be similar to the graph of f of x because it doesn't violate the number of turning points. One more like this, and then I'll talk about something else. If I gave you this function, f of x equals x squared plus 3 times 2x minus 4. In order to know something about the graph, I need to know the degree of the polynomial. And I could, if I'm patient, FOIL this out. If I FOILed this out, I'd go first are x squared times 2x, which is 2x cubed. Lasts, our outers are x squared times minus 4, which is a minus 4x squared. Inners are 3 times 2x, which is a 6x. Lasts are 3 times negative 4, which is a negative 12. That's actually expanded. This polynomial f of x can be expanded to 2x cubed minus 4x squared plus 6x minus 12. So it's a third degree polynomial. So this which means the graph can have no more than 2 turning points. So here's a graph that has no turning points. That could potentially be the graph of this function because that's not violating going over 2 turning points, but something like this couldn't be the graph of f of x because this has 1, 2, 3 turning points. So this has 3 turning points that can't be the graph or even close to the graph. Whereas this little bend here isn't actually a turning point because the function's increasing everywhere. This has 0 turning points, and it could be what the graph of f of x looks like because it doesn't violate having too many turning points. So that's one concept that we have to think about in this section. Another concept that we have to think about is end behavior. And end behavior is what happens to the graph of a polynomial as you get way off to the left of the graph and way off to the right of the graph. So this is a graph of a polynomial, and the ends, the left end and the right end of the graph, so this, I would call this, going off to negative infinity in the x direction, the left end, and going off to positive infinity in the right direction, I'd call the right end. And at the left end, the graph is going down towards negative infinity. So I would say for the end behavior, this graph falls or goes down as it moves left. Or as I move left. So if I'm tracing to the left as opposed to tracing to the right, I'm going to get to the left end of the graph. And as opposed to getting higher, it's getting lower, we say it's falling. For this, the right side of the graph, if I was tracing to get to the right end of the graph, as I'm tracing, I have to go higher. So I would say this graph rises as it moves, or as I move to the right. So for this particular graph that I drew, it's a graph more than likely of a polynomial. It's an unbroken graph, which that is what polynomials are. They have unbroken graphs. And I would say that this one falls as I move to the left on the graph, it rises as I move to the right. Let me draw some more graphs. A graph like this, nice parabola. If I want to describe the end behavior, again, this is the left end of the graph. This is the right end. If I'm tracing to go towards the left end of the graph, my marker is moving down, so I would say it falls as I move to the left, and we usually get lazy. I'll say this, I'll say it falls to the left, which means if I'm tracing on the graph in the direction of negative infinity, the graph is going down. Similarly, if I'm tracing to the right edge of the graph, to trace to the right edge of the graph is still going down. So I'd say this graph falls to the right as well. So this graph falls on both sides. So it doesn't matter what happens in the middle in terms of end behavior. For this particular graph that I drew on the left end, so the left end of the graph is over here. If I'm tracing to the left end of the graph, I'm having to go up as I trace to the left. So I'd say this graph rises to the left, or as I'm tracing to the left edge of the graph, it's going up. And then if I had to trace to the right end of the graph, this graph is going down, so I'd say it falls to the right. I'm getting progressively lazier, including less and less words, but it still has the same meaning. Maybe one more of these. So this graph, again, it doesn't matter how many wiggles it has in the middle to answer what the left and the right end behavior is. You move to the very ends of the graph. For the left end behavior of this, because it's going up to the left, I'd say this graph rises to the left And if I go to the right tail of the graph, it's also going up on the right. So I'd say that this rises to the right. So end behavior describes what the graph does at the extreme left and the extreme right edge of the graph. You do these things in calculus using something called limits. So this is preparing you for calculus. In calculus, you'll actually be given equations, and you'll be doing the limit as x goes to infinity, or the limit as x goes to negative infinity when you're describing the end behavior of a graph of a polynomial. So the concept of whether the graph is going up or down isn't going to change when you get to a calculus class, if you get to a calculus class, but the symbols change, the questions just get odd. But getting grounded in this class with some of the basic concepts, when you get to a calculus class, it'll make it easier to make that transition, because at least you have seen the concepts, and then applying the calculus won't seem so horrible. Okay, so far we have what x, how many humps a graph or turning points a graph can have, and how to describe the left and the right edge of a graph. Another concept is similar graphs. I'll break out my calculator for the first time. If I sketch this graph, f of x equals 2x cubed minus 4x squared plus 6x minus 9. I'm going to graph this just on a real generic negative 10 to 10 viewing window. So I'll break my calculator out, hit my y equals button, clear that junk that's in there, do 2x up arrow cubed minus 4x squared plus 6x minus 9, and hit a graph. That's definitely not a good window, so let me tweak it back to the negative 10 to 10 window. So I know this can't have more than 2 turning points. It looks like it's not going to have any turning points. So I'm going to go zoom, standard, and it's not the ultimate best picture, but for what it's worth, I think this graph has 0 turning points, which is okay. It doesn't have to have any turning points. It just can't have more than 2. And it looks to me like it falls to the left, and it also, so down to the left edge, even though I can't see that far to the left, it looks like it's falling. It also looks like it rises to the right. And I claim that this graph is going to be similar to the graph of 2x cubed. Similar, maybe not in the middle, but if I get out far enough to the left and far enough to the right, these graphs will become almost indistinguishable. So if I graph on the same coordinate system, now 2x up arrow cubed, when I hit my graph button, you start to see that the graphs, although in the middle here, this 2x cubed does something a little bit different, but the higher I go, or the lower I go, the more the graphs look like each other. As a matter of fact, if I bump my window out and drastically change my y's, like maybe change my y's from negative 100 to positive 100, and I look at the graphs together, you start to see a real similarity in the shapes of the graph. In the middle, far away from the end behavior, or close to the origin in some sense, the graphs don't have to look anything alike. But the graph of this more complicated function and the graph of this simple function, when we get in terms of, they'll have the same end behavior, and the graphs will look real similar. As we get higher up, the graphs look more similar. If I change my y's to like negative 1,000 to positive 1,000 and hit graph, again, it's graphing the first function that I made, and now it's graphing the second function that I made, and they even start to look more and more similar. So the variance, the difference between the top graph and the bottom graph is kind of around the origin, or and not for really big values of y in some sense, or not for really big values of x. But the further I get out, the more I zoom out from the graph, the more the graphs don't seem that dissimilar. They seem more similar. Like when I hit my window button, if I hit zoom in standard, in that window, I can definitely tell the graphs apart. They don't look that similar. Like around the origin, it doesn't look that similar. But if I zoom out and change my y's to a really big number, then all of a sudden the graphs start to look alike. And that's going to be the case for any polynomial. Any polynomial, its graph is going to be similar to the graph of the lead coefficient term. So this graph, these two functions, doing something like this, f of x equals, how about 3x to the fourth plus 5x cubed minus 9x squared plus 11x minus 3. Let me just graph that. So y equals clear 3x up arrow fourth plus 5x up arrow cubed minus 9x up arrow squared plus 11x minus 3. Go back to that nice standard window. I know it can't have more than 3 turning points, and in this window I can't get a good grasp of this graph. Let me just make the y's a little bit bigger. Let me change the y's to the hundreds, just so you might get a better picture here. Yeah. So when I look at this graph, for what it's worth, it looks like it only has 1 turning point, which is fine. The most turning points it could have had was 3, 1 less than the highest exponent. Its end behavior is it rises to the left and it rises to the right. And I claim that at some point this graph is going to look like, this graph is going to be similar, at least when I get out far enough, to the graph of just the 3x to the fourth. That the junk after the leading term, or the term with the highest exponent, it does impact the graph. Its greatest impact is in a narrow bound. And if I just graph the function 3x up arrow fourth, when I look at the two graphs next to each other, around the origin, they're definitely not close to each other. But if I take my window and get really big with my window on the y's, again, maybe jump my y's to the thousands, it's going to be hard to, the graphs will start to look more and more like alike. So there's the original graph, and coming up is my next graph of 3x to the fourth. Again, look at the right-hand side is almost dead on, and the left-hand side is pretty close. So the variation in the graphs is not for, really big windows. So I'd say that these graphs are similar once I get into a big enough window. Like in the standard -10 to 10 window, it's going to be real easy to tell the graphs apart. As a matter of fact, I can't even see the bottom of the top graph. So in this window, both the graphs are drawn, and they're not that, they're somewhat similar, but not as similar as if I get bigger. So one of the concepts that we have is, what graph is my graph going to be similar to? So that if you're sketching a graph and you know what a simple graph looks like, then you have an idea of what your graph is going to look like, and you can know if you're way, way off. Okay, still more concepts. It's a really concept-heavy section. So far we have, we know what a polynomial is. We have this as a concept, the maximum number of turning points, and that's 1 less than the highest exponent. So something like this, f of x equals 3x to the fourth plus 5. This can have at most 3 turning points, because 1 less than the highest exponent that I see. We need to know about end behavior. and usually either we say that it either falls or rises to the left depending on what it does, and it falls or rises to the right depending on what it does. And really defined end behavior, it's a calculus problem, so we won't really find it except looking at pictures. So here's an example of a graph that falls both on the left and the right hand side. So I'm going to say this graph, it falls on the left hand side, it falls on the right hand side. And then we have another concept of, what simple function has a similar graph. If I gave you something like super complicated function, f of x equals to negative 5x to the 8th plus 11x to the 7th plus 6x squared minus 2x minus 1, the graph that will have a similar shape is the graph that's just the leading coefficient. So that if I graph this function and I graph this function, if I made the window big enough, the graphs would look similar. If I focus in on the origin, I'm going to see a lot of variation between these graphs. But the farther I go out, the more the graphs look alike. I think the last concept that we have is, that's new anyways, is what happens at the x-axis in terms of the x-intercepts. So I'm going to draw a graph that has two x-intercepts. So this graph has two x-intercepts, this at the point 1, 0 and the point 4, 0. Are where the graph touches or crosses the x-axis. So these are the x-intercepts. They're points on the x-axis that are part of the graph. At the point 1, 0, I say the graph touches but not crosses the x-axis. And at the point 4, 0, I say the graph crosses the x-axis. Let me start to show you how I could make a graph have these for the x-intercepts and how I could change a graph from touching to crossing the x-axis. So I know that this function, f of x equals x minus 1 times x minus 4. It's going to have x-intercepts at 4 and 1. If I draw this on my calculator, getting back to my calculator, if I do x minus 1 times parentheses x minus 4 and do a zoom standard, this graph is going to have x-intercepts at 1 and at 4. There's the x-intercept at 1, there's the x-intercept at 4. For both of the x-intercepts for this particular graph, it crosses. So here, this graph has an x-intercept at 1, 0 and an x-intercept at 4, 0. And at both intercepts, it crosses, my graph does, the x-axis. If I want to make a graph touch but not cross the x-axis, I need to make the factor that produced that x-intercept have a positive or an even exponent. Let me do another graph that has x-intercepts of 1 and 4. If I gave you this, f of x equals x minus 1 times x minus 4 squared. That graph, if I choose to graph it, is still going to have x-intercepts of 1 and 4, meaning it's going to have points at 1 and 4 on the x-axis. And if I do this by just tweaking this function and changing that to x minus 1 times x minus 1 to the 4th, and I hit my graph button, what happens is at 1, the graph crosses the x-axis, but at 4, the graph touches the x-axis and doesn't cross the x-axis. So for this one, it still has x-intercepts at 1, 0, and 4, 0. At 1, it crosses the x-axis. At 4, it touches the x-axis. This exponent made that touching happen. As a matter of fact, if I do this, f of x equals x minus 1 squared times x minus 4 cubed, I can predict what the x-intercepts are and whether the graph is going to touch or cross the x-axis. So this graph, whenever I get to this function, it's also going to have x-intercepts at 1, 0, and 4, 0. And it turns out that if the exponent that makes a factor is even, the graph touches but doesn't cross the axis. If the exponent that makes the x-intercept is odd, it crosses. So this even exponent with the factor makes the graph touch the x-axis. The odd exponent makes the graph cross. In my example that's still on this page, the x minus 1 didn't have an exponent, so it has an exponent of 1. That factor has an odd exponent. Its graph will cross the axis. The x minus 4 gave me an x-intercept of 4. Its graph will touch the x-axis. So if I graphed this function, x minus 1 quantity squared, x minus 1 quantity squared times x minus 4 quantity cubed, I hope when I do the graph, or I know that when I do the graph, that the graph is going to touch at 1 and cross at 4. So when I hit my graph button, at x equal 1, it touches but doesn't cross. At x equals 4, the graph crosses. Again, it doesn't tell me so much what happens between the 1 and the 4 or any place else in the graph. But if I have a polynomial that's in factored form, the exponent that's attached to the factor tells me whether the graph crosses or touches the x-axis at that. So let me do just one more example, then I think we'll be ready to get into the actual problem. So f of x equals x minus 3 quantity fourth times x plus 6 to the 7th. So this graph is going to have two x-intercepts. This right here, if I just set this factor x minus 3 equal to 0, I'm going to get x equal to 3. This graph is going to have an x-intercept at 3, 0 because of that parentheses. The exponent is going to make it, because it's even, it's going to touch the x-axis, but it's not going to cross the x-axis. And the only other x-intercept I'm going to get is by taking the contents of the second parentheses and setting it equal to 0. The second parentheses are good. It's going to give me an x-intercept at negative 6, 0. The exponent, because it's odd of 7, it's going to cross the x-axis. So whenever I get this graphed on my calculator, the graph at 3, it's either going to bounce off the x-axis like that or like that, but it's not going to cross the x-axis. And at negative 6, it's probably going to wind up doing this. It's going to cross the x-axis. I would suspect that when I graph it, I guarantee you the graph is going to cross the x-axis at negative 6, going to bounce off the x-axis at positive 3. And because I've graphed a lot, I think it'll probably do something like this. And maybe the whole function will look something like that. I'm not sure. But if I graph this function, y equals x minus 3 up arrow 4, and then parentheses x plus, I should maybe do a time sign here, parentheses x minus 3 up arrow 4, and then maybe a times just to be safe, x plus 6 up arrow 7. And when I hit graph, there's at my negative 6, it crosses the x-axis there. Here's at my 3. My window's not good enough to see that it reflects off of it. I'm going to have to really blow my window up a little bit. Let me change my y's to the hundreds. And then hopefully we can see the crossing and bounce are reflecting better. It's bouncing off, and it's so steep here. I'm going to have to tweak my window more for you to see this. Let me try to do this. Window, make my x's go from -7 to 4. I'm just not sure on the y's what to do. It's real easy to see that it crosses at the -6. It's hard to see what's happening at the 3 because my window's not suitable for my calculator. Let me graph this on my computer program and show you what happens. So x minus. So I'm just typing the function. I'm not sure you could hear me. I think with this window, it's not going to be terribly interesting. What's happening is the graph is so narrow right here that I can not really tell what's happening, but you can see a little bit. Well, you can't see any better there, I suppose. Let me change my axes. I'm not even sure where to change my axes. Y-axis, -5 to 5. I just can't do much better. What's happening around this 3 is the graph does bounce off. I don't know if you can see there's a slight gap between those. It's a parabola that's so narrow that you can't even tell that it's a parabola. So maybe this wasn't the best function to pick, but you can still see at least that at -6 it crosses the x-axis, and at 3 it touches the x-axis but doesn't cross the x-axis. And I just can't get a good enough window to show you what's happening. That just kind of is what it is. All right, so that's, I think, all the concepts that we need. And I'm going to get into the homework now after a good 30 or 40 minutes of just preliminary, which means this video is probably going to span a couple of lectures as opposed to just one. So we're talking about polynomials, and the first part of problem 2 asks me to do something I know how to do. Very specifically, it asks me to find the x-intercepts. And to find x-intercepts, you just take the function itself and set it equal to 0. And if a factor has a parentheses, it's not really necessary to write the problem without the exponent, but it doesn't hurt. So the algebra to find the x-intercept is I take the function itself and set it equal to 0. For this particular problem, I have 3 different factors that I could set equal to 0. I can set x minus 5 equal to 0, x minus 5 equal to 0, and x plus 2 equal to 0. For the x minus 5s, I could add 5 to both sides and get an x-intercept of 5. The x plus 2, I could minus 2 and get an x-intercept of -2. So for this particular problem, the x-intercepts are the point 5, 0 and the point -2, 0. And then this word multiplicity is basically how many times does a factor occur. And it's something mathematicians use to tell whether the graph is going to touch or cross the x-axis. The multiplicity is going to be the answer to this. And what is the multiplicity? The multiplicity is going to be a word. It's either going to be the word odd or even. and it has to do with the exponent that makes the factor. The exponent that made the intercept of 1 was 2, so I'd say the x-intercept of 5, 0 has even, I'm not going to be able to write multiplicity here with this pen, but I'm going to try multiplicity, because the exponent that made it is even. The exponent that made the factor of x plus 2 is 1, which is an odd number. We say that the x-intercept of negative 2, 0 has an odd multiplicity. And that's everything that's asked for in part A. So I found the x-intercepts by taking the function and setting it equal to 0. Intercepts have multiplicity. Multiplicity is even or odd, and that has to do with the exponent that made the factor. If the exponent is 2, 4, 6, or 8, we say that that x-intercept has an even multiplicity. If the x-intercept is 1, 3, 5, 7, or 9, we say that has an odd multiplicity. And multiplicity determines whether the graph crosses or touches the x-axis. At the 5, 0, because I have even multiplicity, the graph is going to touch but not cross the x-axis. And at the negative 2, 0, because it has odd multiplicity, the graph is going to cross the x-axis. So real quickly, if I just graph this on my calculator, hit my y equals button, hit my y equals button, and graphed x minus 5 squared times x plus 2, and did zoom standard, I should be able to see the x-intercept of negative 2 and the x-intercept of 5. There's the x-intercept of negative 2. The graph crosses at that x-intercept because it has odd multiplicity. There's the x-intercept of 5. The graph touches at the x-intercept of 5 because that intercept has even multiplicity. To figure out the maximum number of turning points and what the graph will look like, what I'm going to do in this expanded form when I wrote the problem without the exponents is I'm going to multiply the first item in each parentheses. So to answer the next two questions, I expanded the original problem to wrote it without exponents, and now I'm going to multiply the first item in each parentheses, which is an x times an x times an x. I don't want to FOIL out this whole entire problem, but if I FOILed out this whole entire problem, x cubed is going to be the leading coefficient, or the term with the leading term, or the term with the highest exponent. So this polynomial, I don't know what it is, it completely expanded, but this is a third degree polynomial. So if I FOILed everything out and got, more after the x cubed, the more after the x cubed wouldn't impact the degree of the polynomial. Any term that came after this, if I FOILed all this out, would have lower exponents. Because this is a third degree polynomial, it has at most 2 turning points. So writing the problem without exponents, multiplying out each of the firsts, tells me what the leading term would be if I did full expansion. And the leading term tells me how many turning points you can have. You can have at most one less than the degree of the polynomial. So this is a third degree polynomial that could have at most 2 turning points. This graph, its graph is going to look like x cubed. So if I graphed that function, my original function in x cubed, they're going to look a heck of a lot different in this window. If I graphed x up arrow 3. In the small window, those graphs aren't going to look anything alike. But if I blew my window up and changed my y's to go like to the thousands, then the differences in the graph occur around the origin, and then the graphs start to look a heck of a lot alike. So the farther out I zoom out, the more the graphs are going to look alike. So to me, those graphs look, a decent amount alike. So I can say that my graph f of x equals x minus 5 quantity squared times x plus 2, it looks quite a bit like the graph of x cubed if I don't use the nice standard window. If I use the standard window, then it's real easy to differentiate the graphs. But in a non-standard blown up window, then I see the similarity that we're asked to describe. Part E wants me to describe the end behavior. I'm just going to steal the end behavior from the graph. I'm not going to do any algebra. I don't have the ultimate best window, but to me it looks like to the left of the x-axis or the left of the y-axis, the graph is going down. So I'm going to say this graph falls to the left, and it looks like the very right edge, the very final thing that it does, it looks like it rises. And see how lazy I'm getting. To the right. So it looks like if I'm tracing off to the left edge of the graph, I'm going to wind up going down. If I'm tracing off to the right edge of the graph, I'm going to wind up going up. Next thing, it says sketch a graph. I'm just going to copy a graph from my calculator and then label the x-intercepts. Easy enough to do. There's the x-intercept at -2. There's the x-intercept at 5. Then it says approximate the turning points. This graph can have at most 2 turning points. I think I'm missing a turning point that's pretty high up. And I'm going to get that turning point in the screen by hitting my window and changing my y max. Because when I look at the graph, there looks like to be a turning point between these 2 parts of the graph, and it looks high, I'm going to change my y max. I'm going to make it really high. I'm going to change my y max to 100 and see if that makes me see the turning point. Oh, you definitely do. So I see the x-intercept at -2, the x-intercept at 5. So let me copy this because I'm asked to sketch a graph and I don't want you to do any more than just copy. But you need to show the features that are appropriate. There's an x-intercept at -2. Here's an x-intercept at 5. The graph looks something like that. And I'm supposed to, so I've labeled the x-intercept. Here's the x-intercept at -2, 0. There's the x-intercept at 5, 0. Nicely, this 5, 0 is a turning point and an x-intercept. The only other thing I need to label on this graph is that turning point. And that turning point likely has a nasty decimal. I'm going to find it on my calculator. This turning point's called a maximum point because it's a local maximum. So I'm going to go second and trace, go down to option 4 that says maximum, use my arrow trace to the left of that high point and hit enter, trace to the right of that high point and hit enter, and then get as close as I can to the high point and hit enter. And my calculator says it's 0.33, 50.81. I'm just going to round everything to 2 decimals. So this point, 0.33 comma 50.81 is the estimation of the turning point that wasn't an intercept. So this is everything that I'd want in terms of sketching a graph. I had to tweak my window from the standard window because at the -10 to 10 window, I couldn't see that turning point. I realized that turning point was higher than I could see. So I changed the y max to 100 because changing the y max makes my graph look higher. I see the -2, 0. I see the 5, 0. I found that. Done with the f part. Now I'm going to go to the g part. The g part wants me to describe where the function is increasing and decreasing. And we've done this before. If I want to break this graph up, the x-intercepts have nothing to do with whether it's increasing or decreasing unless they're a turning point. So this graph, if I looked at it in terms of increasing, these are the regions where the graph is increasing because as I move from left to right, I'm making my marker go higher. This first region is from the far left edge of the x-axis, which is -infinity, to the x-coordinate of that local maximum, which is 0.33. And this region goes from x equal to 5 to the edge of the graph at x equal infinity. So these are the regions where the graph is increasing. If I wanted to show the region where the graph is decreasing, this is the region where it's decreasing from the local maximum to the local minimum. And if I wanted to say where this graph is decreasing as I move from left to right, it's decreasing from 0.33 to 5. Increasing and decreasing only get round brackets. So that's everything that's needed for problem 2. So these problems are rather involved, but once we do enough of them, they won't hopefully feel so bad. Okay, so problem 4 wants me to list the x-intercepts and their multiplicity. I'm going to set the function equal to 0, and I'm going to expand it. So I'm going to go 3x minus 2 times 3x minus 2 times x plus 1 times x plus 1 5 times. The reason I'm expanding it is it's going to help me do part C and part D. To find the x-intercept, it's enough just to take the unique factors and set them equal to 0. The unique factors are 3x minus 2 and x plus 1. If I set the 3x minus 2 equal to 0, it's going to take me 2 steps. I'm going to add 2 and get 3x equal to 2. And then I'm going to divide by 3 and get x equal to 2/3. And that's going to give me an x-intercept at 2/3 comma 0. The x plus 1, I'm going to minus 1 from both sides and get an x-intercept at negative 1, which is at negative 1, 0. So the x-intercepts are 2/3 0 and negative 1, 0. The exponent that made the 3x minus 2 is a 2, which is an even number. So for that 0, or that x-intercept, I use the word zeros and x-intercepts interchangeably. This one has even multiplicity. The x plus 1 that gave us x-intercept of negative 1, 0, its exponent was odd, or a 5, so we say this has odd multiplicity. Which means when I go to graph it, at the x-intercept of 2/3 0, the graph is going to touch but not cross the x-axis. And at the x-intercept of negative 1, 0, because it has odd multiplicity, the graph is going to cross the x-axis. So the graph is going to have 2 times that it's on the x-axis. One it's going to touch, the other it's going to cross. Now I'm going to multiply the first in each one of these parentheses. So I'm going to multiply a 3x times the 3x times 5x's. And if I do that, I multiply the 3's together and get a 9, and there's 1, 2, 3, 4, 5, 6, 7 x's. This polynomial is a 7th degree polynomial. Which means it could have at most 6 turning points. The maximum number of turning points is 1 less than the degree, so this has at most 6 turning points. You can't have more turning points than the degree of the polynomial. And for very large values, this graph is going to look like the graph of my function. If I go out, zoom out far enough, is going to look like the graph of 9x to the 7th. I'm slightly worried that it's going to be hard to find the turning points because of how this exponent 5 and this being a 7th degree polynomial, sometimes it's very hard to find turning points. So we'll see how we succeed or not when I get into the algebra necessary to find, or the calculator work to find the graph and the turning points. So problem 6 says describe the end behavior. Sketch a graph, state the intervals where it's increasing and decreasing. All of these, I need a picture. So I'm going to take my calculator out, hope that I can see from a nice sane window everything that I need to see. So I'm going to go 3x minus 2, up arrow, or squared, and then times x plus 1 to the 5th. I'm going to go back to a zoom standard. I like starting off with a standard window. I hope that it gets me something reasonable. I probably, oh, that's not good. I probably am going to have to tweak my window in order to see a good picture. But for end behavior, I'm good. I think the left edge right here, it looks like it falls to the left, and it looks like it rises to the right. So just by that not so great graph, I can tell that the left edge is going down. So I'm not doing any algebra. I'm just looking at the picture and making a guess that that's what it's doing to the left. And to the right, it looks like it's rising to the right. Looks like everything that interesting that happens to this graph happens right around the origin. So instead of going to expand, I'm going to narrow in. On the last graph, I could tell that the maximum was way up high, and so I changed my Y max. Here, it seems to me everything that's interesting is happening is around the origin. I know from my algebra that the x-intercepts were at 2/3 and at -1. And at -1, the graph crossed, and at 2/3 it touched, and I just can't see in this window what's going on. I'm going to crunch my x's because it doesn't look like anything that's interesting is happening maybe outside x between -3 and 3. Similarly, I'm going to crunch my y's because it doesn't look like there's anything happening too high or too low. So I'm going to change my window. On my x's, I'm going -3 to 3. And on my y's, I'm going to go -3 to 3 on the y's. I like square windows and see if I see anything interesting. And I start to see a much better picture. So there's the graph crossing the x-axis at 2/3. There's the intercept graph touching at -1, 0. I didn't go up high enough. I need to go up a little bit higher here. So I'm going to change my y max maybe to like 6. And now I think I can see everything that I need to see. So it looks to me like there's only 2 turning points. This little hump here, that's actually not a turning point. So let me copy this graph. So this graph looks something like, so it goes through 2/3 on the x-axis. So I have an x-intercept at 2/3, 0. I also, whoops, I take that back. I have an x-intercept at -1, 0, and it's crossing at -1. And at 2/3, 0, it's touching. Really, John? So now I'm just going to copy the graph from my computer or my calculator, and I might as well do it in a color that shows up. So it looks to me like it's just doing this and that. So there's a certain art to getting the window appropriate, and that has to do with just kind of looking at the graph and deciding where the interesting features are. So it looks to me like I have almost everything labeled except that maximum point, because that point looks like to be the point 2/3, 0. There's 2 turning points, and that turning point I'm going to get by going second calc, going to the maximum feature. I trace to the left of where the high point is and hit enter, trace to the right of the high point and hit enter, and then get as close as I can to the high point and hit enter. And my calculator tells me this is 0.19, 4.88, and I'm just rounding the 2 decimals again. So I'm estimating this turning point to be the 0.19, 4.88. Turning points are maximums or minimum points. You need calculus to find them via algebra. Again, this is just prepping you for if you get into a calculus class, what you're going to see in a calculus class. In a calculus class, you'll be asked to do this entire graph completely without a calculator, and you'll be able to do it. But the skills that you need to do that graph are in calculus, not algebra skills. So again, so where is this graph increasing and decreasing? I'll just break the graph up into its components. This region of the graph and this region of the graph is where it's increasing. That's the region between -infinity and 0.19. And then again between 2/3 and infinity. The x-intercept at -1, the graph doesn't change directions. That's not a turning point. So I'm going to say this graph is increasing from negative infinity to 0.19, and then again from 2/3 to infinity. And where the graph is decreasing is in a similar region, this region between 0.19 on the x and 2/3. So this graph is going to be decreasing in that little region, and that little region is from x equal to 0.19 to x equals 2/3. That's everything there was for that problem. So it turns out that there's not a lot of algebra for these problems, which make them kind after you get into the groove. At first they seem a bit overwhelming because there's so much going on, but it's not going to be so bad once we get through enough of them. So finding the x-intercepts, to find the x-intercepts, I'm going to expand because it's going to help me eventually. So to find the x-intercepts, it's enough just to take each unique parentheses and set it equal to 0. The unique parentheses are the x squared minus 5 and the 2x plus 5. I'll set them each equal to 0. You have to remember the algebra for solving this x squared minus 5. That doesn't factor, so I'm going to solve with square roots. I'm going to add 5 to both sides and get x squared equal to 5. And then I'm going to go square root plus or minus square root. And this one gives me x equals plus or minus the square root of 5. So that's going to give me square root of 5, comma 0, and the negative square root of 5, comma 0. Because this came from an exponent that has 2 as it, each one of these is going to be an even multiplicity, and the graph is going to touch the x-axis for those. So each one of these, 0, square root of 5, and negative square root of 5, came from something that had a multiplicity that was 2, which is even. So the graph is going to touch. For this next one, for the 2x plus 5, I'm going to minus 5 and get 2x equal to negative 5, and divide by 2 and get x equal negative 5 halves. And at this negative 5 halves, comma 0, the exponent that made that was 1, so that has an odd multiplicity. So there's 3 x-intercepts at both the square root of 5, comma 0 and the negative square root of 5, comma 0. The graph is going to touch but not cross. And at the negative 5 halves, comma 0, the graph is going to cross. So it's factored. I set each factor equal to 0. Solve using the algebra I need to solve. For the next part, I'm going to multiply in the expanded form all the first stuff. So I'm going to multiply x squared times 2x. The 2 is going to hang out. There's 2, 4, 5 x's. I'm adding those 2 x's plus those 2 x's, the exponents, and this 1. So this multiplies out to be 2x to the 5th. So this is a 5th degree polynomial. This says 2x to the 5th. So here we have at most 4. I'm going to abbreviate TP for turning points. And if I zoom out far enough, this graph is going to look like f of x equals 2x to the 5th. Okay, when I get into the graphing, I probably need to know what the square root of 5 is, so I know where to find those numbers. Let me do this. Second square root of 5. Square root of 5 is 2.23. This is kind of unfortunate that I'm going to have x-intercepts at positive 2.23, negative 2.23, and negative 2.5. These two x-intercepts are going to be really close to each other. And it's going to make it really not good in terms of getting a window. It's going to make me struggle to get the window. I should have made this 2x plus 5 something that had an x-intercept that wasn't so close to that. So if I look at the decimal forms of my x-intercepts for what it's worth, this is going to be at 2.23 comma 0. This one's going to be at negative 2.23 comma 0. This one's going to be at negative 2.5 comma 0. That's not desirable. Having x-intercepts that are that close to each other makes it hard on our graphing calculators to see everything we need to see, but let me see what I can do. So I'm going to sketch a graph. Easy enough to get my end behavior, sometimes really hard to get the window that I need. And as I was writing the key for the odd problems, I literally changed problems while I was making my key, just because it was just insanely hard to get a viewing window that was going to work. So I'm going to go zoom in standard and hope like heck I can force a viewing window that works, but I'm worried. Yeah. Yes, this is not good at all. So first of all, it's supposed to have x-intercepts at 2.23 and negative 2.23 and negative 2.5. I don't see those so well. Let me try to tweak the window. And I don't know if I can make my calculator get this. So let me, oh gosh. I know I need to zoom in on this region, and I might have to, I think there's a maximum way up top that I can't see, but I don't think I can see very well what's going on here. Let me change my window. Let me change my window to see maybe what's happening right here first. And that's in that little region between negative 2.5 and negative 2.23. So I'm going to magnify this region. I'm going to magnify that region the best I can, and then I'm going to go up high. I'm going to try to get this graph in 3 segments. First thing I'm going to do is just look at the region between negative 2 and negative 3 on the x's, and negative 1 and positive 1 on the y's. That's going to show me what's happening. Oh, yes. That's going to show me what's happening negative 3 and negative 3 and negative 2 on the x's, and negative 1 and positive 1 on the y's. That's going to show me what's happening in that region between the negative 2.5 and negative 2.23. So this is way more advanced than we might need to be in terms of the skill level that you need to have right now. But it's good to see me struggle a little bit, because you're going to struggle when you do these by yourself. So this is the region between the negative 2.5 x-intercept where it crosses and the negative square root of 5 where it touches. So I'm going to just blow that up. And so in this region, the best I can tell is it does that. So that gives me a nice go of it. I'd also like to look at the square root of 5 region, which is at 2.25 or 2.23. I'm going to change my window and see what happens if I just look at the region between, let's say, 2 and 3. And so I'm micro-focusing on that region right there. And when I hit graph, I see perfectly what happens there now. So at this is at the square root of 5 where it reflects off. So right there, it does that. There's no way for me to get one window to show all the features, because the calculator just doesn't have enough pixels to do that. The last thing I need to do is I'm going to go back to a standard window. So I've blown up better what happens around the x-intercepts to the left of the y-axis. And my calculator does horrible there unless I really focus on that. The last thing I need to do is get this little top part. To get that top part up there, I'm going to expand my window by changing a y max to a big number. I'll change it to 100. And I even need to go higher than 100. I see, nice, I can finally see that what's happening at the square root of 5. I need to go higher than 100. I'm going to change my y max to 200. And hit graph. There, I can finally see. So what the graph gets really high and does something like that. There's no problem on your homework that you need to have 3 different windows to see all the pieces. I fixed those problems properly. And I'm pretty sure that if you look at my answer key of the solutions manual, I wrote the window that I used. So I know that these points are the x-intercepts at negative 2.5 comma 0. This is the negative square root of 5 comma 0. This is positive square root of 5 comma 0. Last thing I need to get is that point there. That's a maximum. I do that by going second calc, going down to number 4 that says maximum, trace to the left of the high point and hit enter, trace to the right of the high point and hit enter, and then get as close as I can to the high point and hit enter, and I get 0.41 comma 135.88. That's the best I can do, and this probably should really be way up here, but this is accurate enough. It shows the turning points just fine, and no, it doesn't. I missed the turning point. There's actually a turning point right there that I didn't get. I need to go back to this window, the really crunched window. So window from that window I did from negative 3 to negative 2, and then I did like negative 1 to 1. There's a turning point here that I missed. That turning point's another maximum. I'm going to get that turning point as well by going second calc maximum, trace to the left of that high point, hit enter, trace to the right of that high point, hit enter, and then get as close as I can to that high point and hit enter. And that is the point, negative 2.4.12 I'm going to write. So this is negative 2.4 comma 0.12. I'm going to write all of this on another piece of paper because I'm not content with that. So this is a better picture. So this graph is supposed to look something like this. So it has an x-intercept at negative 2.5 comma 0. And then a turning point right there. That turning point is at negative 2.4 comma 0.12. And for what it's worth, that region of the graph is a region where the graph is increasing. That whole region between the left edge of the graph and the first turning point is a region where the graph is increasing. And that's from negative infinity to negative 2.4. Then the graph turns around from the high point to this x-intercept at the negative square root of 5 comma 0, and in that region the graph is decreasing. So between the local maximum and this x-intercept, which is a local minimum, between x equal negative 2.4 and x equal negative square root of 5, the graph is decreasing. Then the graph shoots and goes way high, and that's this region. And in that region, from this x-intercept at x-coordinate of negative square root of 5 to that local maximum, the graph is increasing. So again, it's going to be increasing from 0.41 to 1, from negative square root of 5 to 0.41. Then the graph turns around and decreases to the x-intercept at square root of 5 comma 0. So for that region, from 0.41 to square root of 5, the graph is decreasing again. And then finally it turns around from the square root of 5 on forever, and it increases again. So this is a better picture of the graph, and when I go to answer the increasing and decreasing, this region right there it's increasing, that region right there it's increasing, and that region right there it's increasing. This region it's decreasing, In that region, it's decreasing. It was overkill for this problem, but it's good enough. So let me tack those words on to my answer. So my graph is here. It's reasonable. This graph is increasing. I'm going to do an up arrow for increasing from negative infinity to negative 2.4. And then again from the negative square root of 5 to positive 0.41. And then again from the square root of 5 to infinity. It's decreasing. I'll write a down arrow for that from negative 2.4 to negative square root of 5, and then again from 0.41 to square root of 5. I forgot to do the end behavior, but it's on this side it's falling, and that side it's rising, so I'm going to say it falls to the left, probably falls, and then rises to the right. Should maybe not be glad, but the fact that this isn't a calculus class, we did a light version of this problem. You'll do problems this complicated and more complicated in calculus. You'll be asked to do everything that we just did without using your calculator to find the things that we use our calculator to find. And it's going to be harder, but having the base knowledge that you're getting now is going to help you hopefully tremendously if you have to take brief or regular calculus, because you spend a lot of time analyzing the graphs of polynomials in brief calculus. Really, I'm going to change this problem before I even get started. I'm going to change this to x squared minus 2 to the first power, and that's the square root of 2, that's 1.4, and this I'm going to make, so let me change this whole problem because I realize what I'm going to have happening. Let me make this nicer. I'm going to make this x squared minus 4 to the first power, and how about 2x minus 10 squared. Much better. I think much better anyways than the original problem. I'm starting to visualize the algebra and just seeing that wasn't going to be good. So I'm going to find the zeros and the multiplicities by expanding this, going x squared minus 4 times 2x minus 10 times 2x minus 10. I'm going to set each of the factors equal to 0. Bugs the heck out of me that I didn't leave myself enough room to do this. But the two factors are x squared minus 4 and 2x minus 10. For the x squared minus 4, I can solve by factoring. I can solve it by factoring this to x plus 2 times x minus 2. Then I'll go x plus 2 equal to 0, x minus 2 equal to 0. Subtract 2 from the x plus 2 and get negative 2. Add 2 from the x minus 2 and get x equal to 2. For the 2x minus 10 equal to 0, I'm going to add 10 to both sides and get 2x equal to 10. Divide both sides by 2 and get x equal to 5. So there's going to be 3 x-intercepts. The x-intercepts are going to be negative 2, 0, positive 2, 0, and positive 5, 0. Each of these came from a parentheses with an exponent of 1. They have odd multiplicity. And you'll be able to tell from the graph if you've messed up on the multiplicity. If the graph doesn't cross the x-axis and it touches the x-axis, you were supposed to write even. At 5, that exponent that came from it is 2, so it has even multiplicity. So now at the point negative 2, 0, the graph better cross. If the graph touches but doesn't cross, I'm going to change the word to even and not even know that I did it wrong. Similarly, at 2, 0, it should cross. And at 5, 0, because of the even multiplicity, it should touch. In this expanded form, I'm going to multiply the first. I'm going to multiply x squared times 2x times 2x. Multiply the 2's and get a 4. Add the exponents on the x's and get another 4. This is a fourth degree polynomials. The maximum number of turning points is going to be 3. And this graph at the edges, if I blow it up, it will look a lot like 4x to the fourth. Between or around the intercepts, it may not look anything like 4x to the fourth, but if I blow it up, it'll look a lot like 4x to the fourth. So now I'm going to graph this, probably with just a nice standard window. Go back to the zoom standard. Hopefully that window is suitable, but it may or may not be. So I'm going to go y equals clear, and then do parentheses x squared minus 4, and then parentheses 2x minus 10 squared. Hit my graph button. Hopefully I see a nice graph. I can see good things here. I can see that it crosses at -2. I can see that it crosses at +2. And I can see that it touches at 5, but the window's not suitable to see. So I need to go higher to get this maximum up here. So I'm going to change my window, changing the y max. I'm going to change it up to 100, leaving everything else at the 10s, and see what happens in terms of my picture. Good things happen. I see the -2, the +2, the crossing, the 5, the touching. I see a maximum here, a minimum there. There's another minimum down lower because I can see that I need to go lower. To go lower, I change my y min. I'm going to change my y min to a -100 and see what happens from that. It's not low enough. I I need to go way down here, and let me see by how far down I have to go. Let me change my y min to maybe like -500 and see if that helps. Yes, it does help. So this window is suitable for seeing all the features. So this is, again, this is the process that I go through. I had that standard window, zoom standard, and I looked at it and said, well, what am I missing? I immediately knew I was missing a maximum, so I made my y's go higher. And then after I saw I was missing a maximum, I found I was missing a minimum. I made my y's go lower. And there's no rocket science to this. This is just playing until you can see all the features that you care to see. So now I can see everything. I'm going to copy this graph. For the end behavior, this edge and that edge, it's both going up. So I'm going to say it rises to the left and to the right. So the graph that I'm going to produce looks something like this. It crosses the x-axis at -2, 0. Then it turns, crosses the x-axis again at the x-intercept of +2, 0, and turns around, and then at the intercept of 5, 0, touches. So that's that. And I don't know how good it is, but it's good enough. And so for the end behavior, the left and the right end, it's going up. So I'm going to say it rises to the left and rises to the right. Now I need these turning points. I need 1, 2, there's 3 turning points. One of them's at that 5, 0, so that I don't have to find that. This turning point down here is a minimum. So I go second, calc, go down to number 3 that says minimum, trace to the left of the bottom point and hit enter, trace to the right of the bottom point and hit enter, and then as close as I can to the bottom point and hit enter. And it tells me, I'll round to 2 decimals, -0.64, -456.84. So this point right here is the point -0.64, comma, -456.84. This point up here is a maximum. I'll find it by going second, calc, maximum, trace till I get as close as I can to the x-intercept, or the high point, to the left of it and hit enter, to the right of it and hit enter, and then as close as I can to it and hit enter, and it tells me that it's the point 3.13 or 3.14, comma, 81.09. I'm just rounding to 2 decimals just because I have to round at some point. So there's a nice picture. Now I'm going to describe the intervals. This first leg of the graph from -infinity to that low point, it's decreasing. So in the decreasing part of the answer, it's between -infinity and -0.64. As I move from left to right, the graph is decreasing. And then from this -0.64 up into that maximum point of 3.14, the graph is increasing. So it's going to be from negative 0.64 to 3.14. Graph turns around again from 3.14 to 5 and decreases. And then lastly, from 5 to infinity, the graph is increasing. So hopefully the increasing and decreasing part isn't something you've forgotten. Lots of increasing and decreasing in calc, so the more I show you, the better it's going to be. I know I'm running shy on time. Let me try to do one more. I'm going to check to see if my video is working. Otherwise, I'll stop. Still going. Again, I'm going to tweak this problem because I'm just worried about the window. And I'm going to change this just to be x squared plus 5 times 2x plus 5, as opposed to making it have the square. And let me think about that. 5, I don't like having the 5. And let me change this to, well, that's actually okay. This is actually interesting and okay just like that. Dumping out that exponent will make the graph just saner. The exponents just sometimes make the windows really hard to get, and you've got to tweak too much. I'm trying to make things that don't need as much tweaking. So finding the x-intercepts, I'm just going to take the x squared plus 5 and set it equal to 0. The 2x plus 5, set it equal to 0. For the x squared plus 5, that doesn't factor. I'm going to minus 5 from both sides. When I minus 5 from both sides, I get x squared equal to negative 5. And then I'm going to go square root plus or minus square root. This is going to give me x equals plus or minus I square root of 5, because the square root of a negative gives me an I. I's aren't going to show up on my graph. This x-intercept I'm not even going to write because it's not actually the graph. I don't show an I on my graph. That's not going to be an x-intercept that I could see unless I was graphing imaginary numbers, which I'm not. So this is not going to give me an x-intercept because it has an I. The only place this graph is going to cross the x-axis is the answer that I get from this. When I set 2x plus 5 equal to 0, I minus 5 and divide by 2. I get x equal to negative 5 halves. The only x-intercept is the point negative 5 halves comma 0. The exponent that came from this was odd, or it's 1, so we say it has odd multiplicity. The only place this graph is going to cross the x-axis is at the point negative 5 halves, or negative 2.5 comma 0. And because of the odd multiplicity, the graph is going to cross the x-axis and not touch the x-axis. I'm going to multiply the first items in each parentheses to do the next part. I'm going to go x squared times 2x, which is going to be 2x cubed. That's a third degree polynomial, so this has at most 2 turning points. I'm going to make turning points TP. And if I made a big enough window, I wouldn't be able to distinguish my graph from the graph of f of x equals 2x cubed. At least they'd look a lot alike. Now I'm going to graph this, hopefully with a nice standard window. Go back to the zoom standard just because I like a standard window if I can make it work. So I'm going to go y equals, new version of the problem is parentheses x squared plus 5 times parentheses 2x plus 5. Hit my graph. Hopefully I can see all my maximums and minimums. I can't. This graph only crosses the x-axis right there. It doesn't cross the x-axis again. Looks too much like a line. Let me go higher and lower. I might not have any turning points. I don't have to have turning points, but let me make my y's go higher and lower and see what happens if I, yes, that's, so I don't get a turning point. The graph doesn't. It increases forever. So this is the best I can do. The more I blow up my window to see, like if I blow the y's up to the hundreds, I'm not going to see, the graph's not going to turn back around on itself. So this graph right here, that's not a turning point. It kind of flattens out and then goes faster again. This is a reasonable graph. I'm going to copy this on my page that asks for my graph. Even the graph at the negative 10 to 10 window wasn't horrible. It doesn't have as much bends in it. But my x-intercept is at negative 5 halves, comma 0, which is at negative 2 and a half, comma 0. And the graph looks something like that. These aren't turning points. They're called inflection points in a calculus class, which you'll find those in a calculus class, but not in here. So that's a reasonable graph. The end behavior, the left edge, I'll say it falls on the left side, and on the right side it rises. There aren't any local maximums or local minimums, so the graph never turns in direction. And it always, as I move from left to right, it's always increasing. For this graph, it never is decreasing. It's increasing from the far left edge to the far right edge, because as I'm drawing this graph, my pen is constantly going up and to the right. It's never going down and to the left. So the graph is always increasing, and it's never decreasing. One more, and then I'll pause the video and do a second half to this tape. How far do I need to go? There's a 12. There's a 14. Oh, yes. Also, I get crazy on these. 16. 18. And then more stuff. 20. Okay, so this is going to be an all-day affair. Sorry about that. Again, let me tweak this down. Let me make this x squared plus 2 to the first power. And what the heck, I'll make this 2x plus 1 to the first power, just to make this. I like the squares, okay. So I'm going to do x squared plus 2 times 2x plus 1 squared as the function, just again to make things reasonable when I get to my window. For the x-intercepts, I take each parentheses where I can expand this. It says x squared plus 2 times 2x plus 1 times 2x plus 1. I'll set the x squared plus 2 equal to 0. And the 2x plus 1 equal to 0. For the x squared plus 2, I minus 2 from both sides and get x squared is negative 2. I square root plus or minus square root. This gives me x equals plus or minus I square root of 2. Because there's an I, that doesn't give an x-intercept. For the 2x plus 1, I minus 1 and get 2x is negative 1, and then divide by 2 and get x equal negative 1/2. So the only x-intercept, just like the last problem only had one x-intercept, is at the point negative 1/2, comma 0. The exponent from that 2x plus 1 was even, so that at the x-intercept of negative 1/2, 0, which had even multiplicity. I don't know if I wrote the multiplicity on the last ones as I did. It's going to touch but not cross the x-axis there. In this expanded version, if I multiply the first x squared times this 2x times that 2x, that gives me 4x to the 4th. This is a 4th degree polynomial. We have at most 3 turning points, and if I get into a big enough window, I won't be able to distinguish my graph that easily from the graph of 4x to the 4th. Let me graph this x squared plus 2 to the first power times 2x plus 1 squared in a nice standard window. So x squared plus 2 parentheses 2x plus 1 squared, and hit my graph button with a stand and have a standard window set, I don't think. Zoom, standard, maybe I set it back up. I think this is a reasonable window, actually. It looks to me like the graph, there's the x-intercept at negative 1/2, 0, and it doesn't look like it turns back around. Let me stretch the graph to make my y's go real high for a second. I'll make my y max go to 100 to see if anything odd happens real high. Nothing looks like, it doesn't look like it turns around up high anywhere. And let me scrunch my y's real low to focus in on the x-axis real well. And I think I have a pretty decent picture here. So this is just almost looks like a parabola. It's a pointy parabola. So the graph of this function should look something like this. Again, with a calculator and not doing calculus, that we're limited. It has an x-intercept at -1/2, comma 0. The graph touches but doesn't cross, and that's the whole thing. It's almost like a parabola. For the end behavior, this here, it rises on that side to the left, also rises on this side to the right. Nicely, the only turning point is an intercept, so there's no more points to find. This region of the graph as I move from left to right is decreasing. So that region, I can define that as from -infinity to -1/2 in terms of the x's. And this region where it's increasing is from x equal to -1/2 to x equals infinity. I'm going to see if my video is still going. I might try one more. Oh, and it is. So one more, because it's still the same style of problem. And again, oh no, it's not. So this is a good place to stop. So once I get to 14, the problems don't have the parentheses. They're not going to be really any different. They're actually probably slightly easier than the problems that we just did. So that was a really long video just to get done with 6 problems. And be prepared for more length as you get into the rest of this section. And let me see what we have left. We have more graphs that we've just been doing. Things that aren't factored actually makes them a little bit easier, I think. Those won't be anything. There won't be anything new in those other than I'll have to factor. And then the last problems, create my own polynomial. Those aren't that bad. Yeah, not that bad. Now, so the rest of it won't be near as bad as what you've just been through. So we kind of threw the bulk of the grunge for this section. This is one of the harder sections, if not the hardest section in this chapter. Actually, there's a lot of grunge in this chapter, so maybe I'm lying saying this is the hardest, but maybe it's one of the harder ones. Okay, so I'll pause this, go have breakfast, come back and finish up the section, and maybe be able to do the rest of it in an hour and a half.